radio waves, this is a different problem, right? I was like, oh, I think I didn't catch that when I was first doing it. But notice that this is now 56 kilometers, right? And the radio waves are polarized. So the fact that they're polarized really should give us a clue that we should be using a polarization formula, right? Okay. So the plane of polarization of these waves is parallel to the transmitting antenna. An identical antenna is used for reception, right? Suggest why the receiving antenna needs to be parallel to the transmitting antenna. Okay, well, okay, so the same way that antennas transmit, they also receive energy, right? So on this transmitting antenna, we're pumping electrons up and down, up and down, up and down, and crossing this changing electric field, which is, by the way, the electric field is the direction of the polarization. And it's going up and down. It's not going side to side. It's not going in and out of the page here. It's going straight up and down. And so the receiving antenna, in order for that electric field to, but we don't know about electric fields, right? To actually pump it up and down and get the maximum potential, it needs to be parallel to that electric field, right? So the electric field can fully pump the electrons up and down. So that's one explanation. Another explanation is that this is polarizing, and so the receiver acts like a polarizing filter, in which case we could use, I think it's called Malice's law or something like that. It's like not malice as in hatred, though. Okay. But basically that the transmitted intensity is the original intensity times cos squared theta. And of course this is cosine, right? So the biggest cosine is 0 and it sharply drops off after that, right? Okay, so this is equation 4.3.3, right? Anyway, that use some explanation there. See if you can get both marks.